and welcome to Alpha Omega training videos. In this video, we are going to model a gas splitter and then investigate the erosion phenomenon all over the domain using ANSYS Fluent software. Stay with us. To start the simulation, I open the ANSYS Fluent software, and here from the file and read, I can import the keys and data files. Here's the gas splitter case. By selecting it, after a few moments, the keys and data files will be loaded. Okay, that's it. Now I can see the work done in the console. So I can understand that the keys and data files are imported successfully. In order to display the geometry of the solution, we can hit the display mesh option here, or the display button here, or in the domain tab, the display option. Here you can select your desired surfaces and display. Okay, this is the geometry of the project, a gas splitter. The inlet boundary condition is here. Outlets, the fins, and outer walls. And we can also see the elements on the surface of the geometry by enabling the edges under the options. And after hitting the display, we can see the elements all over the domain. Okay, here we have the check button. This option is used to check the quality and validity of the mesh. It checks for several potential issues such as negative cell volume, non-positive face area, highly skewed faces, and more. It's important to note that a good quality mesh is crucial for obtaining accurate and reliable results for your simulation. Here the process is done, and there's no issue in the mesh file. After that, we can select the report quality. After clicking the report quality button, the ANSYS Fluent will give us two parameters, which is the first one is minimum orthogonal quality, and the second one is maximum aspect ratio. In ANSYS Fluent, the aspect ratio refers to the ratio of the longest edge to the shortest edge in a cell. It's an important metric for mesh quality. Fluent can handle high aspect ratio cells, but for better accuracy, it's recommended to keep it below 100. However, in boundary layers, it can be several thousands. Also, the orthogonal quality is a measure of the cell's deviation from a perfect shape. The range is 0 to 1, where 1 represents a perfect cell. Lower values indicate poor quality, potentially leading to inaccurate results. It's crucial to maintain high orthogonal quality, preferably above 0.1, to ensure accurate and reliable simulations. Here you can see that we have a high quality mesh file. Furthermore, we have the solver type, which is selected as pressure based. The pressure based solver in ANSYS Fluent is primarily used for incompressible and mildly compressible. This solver uses the pressure correction method to solve the Navier-Stokes equations. The steps involved include guessing the pressure field, solving the momentum equations to obtain a velocity field, and then correcting the pressure field based on the divergence of the velocity field. The process is then iterated until a converged solution is found. This solver is efficient and suitable for a wide variety of flow problems. The velocity formulation is absolute, and in case of time, the solution is steady. Also, the effects of gravity are neglected. By double-clicking on the models, here we can see all the models available in ANSYS Fluent software. Here in the viscose section, there are several turbulence models available for use. These include the Spallert-Allmaras model, K-epsilon models, K-omega models, Reynolds stress models, and large eddy simulation models. These models help simulate and predict the behavior of turbulent flows. Each model has its strengths and weaknesses, and the choice of model depends on the specific application and the level of accuracy required. What is selected for our solution is the K-epsilon model, which is a two-equation model and realizable. This model offers an improvement over the standard K-epsilon model by providing superior performance for flows involving rotation and boundary layers under strong adverse pressure gradients, separation, and recirculation. The realizable K-epsilon model is based on the transport equations for the turbulence kinetic energy and its dissipation rate. The term realizable means that the model satisfies certain mathematical constraints on the Reynolds stresses consistent with the physics of turbulence. The benefits of using this model include its robustness, economy, and reasonable accuracy for a wide range of turbulent flows. The next model is the discrete phase model. This model is a powerful tool used to simulate the flow of discrete particles or droplets in a continuous phase. It's particularly useful in multi-phase flow simulations like particle tracking. Okay, in the discrete phase model window, we have a bunch of options, which the first one is interaction with continuous phase. The interaction with continuous phase option is a setting that allows users to model the interaction between the primary phase or the continuous phase and the secondary phase, which is the discrete phase, in a multi-phase flow. This interaction can be in the form of drag, lift, virtual mass, wall lubrication, and turbulent dissipation forces. Next option is update DPM sources every flow iteration. When this option is enabled, the sources of mass, momentum, and energy from the discrete phase to the continuous phase are updated after each flow iteration instead of after a complete DPM iteration. This can potentially lead to a more accurate solution, especially in cases where the interaction between the phases is strong. However, it may also increase the computational cost. Here we have the DPM iteration interval. This option is a parameter that determines the frequency of particle tracking calculations in a discrete phase model simulation. If you set the DPM iteration interval to, for example, n, Fluent will perform particle tracking after every n flow iterations. This means if you have a high iteration interval, the particle tracking will be less frequent, which might speed up the simulation, but at the cost of accuracy. On the other hand, a low iteration interval will result in more frequent particle tracking, leading to a potentially more accurate but slower simulation. It's a balance between accuracy and computational efficiency. Also here we have the tracking parameters, which the first option is maximum number of steps. This option is used to set a limit on the number of steps that a tracked particle can take. This parameter is particularly useful in controlling the computational time and resources. If a particle's trajectory is complex and requires many steps to compute, it may consume a significant amount of computational resources. By setting a maximum number of steps, you can ensure that the computation completes within a reasonable time, albeit at the risk of truncating the particle's path if it requires more steps than the specified limit. The next option is step length. After the tracking tab, we have the physical models tab, which ANSYS Fluent offers a bunch of tools to help us simulate more complex projects. Here under the options, the first option is the Softman lift force. This force arises due to the velocity gradient around the particle moving in a viscous fluid. It's perpendicular to the relative velocity and the rotation direction of the fluid. The virtual mass force comes into play when the fluid surrounding a particle accelerates or decelerates. The particle tends to resist this change due to its inertia, leading to the virtual mass force. The pressure gradient force is due to the variation of pressure around the particle. The pressure gradient force acts in the direction of decreasing pressure. Here we have enabled the erosion accretion option to investigate the erosion all over the surfaces of the project or our gas splitter. These models account for mass transfer between the particle and the continuous phase. Erosion refers to the removal of particle mass, while accretion represents the addition of mass. Next option is two-way turbulence coupling. In this model, particles not only get affected by turbulence, but also influence turbulence in return. This two-way interaction is significant when the particle loading is high. The DEM collision or discrete element method collision model handles particle-particle interactions. It's used to predict the motion and collision of a large number of particles. The stochastic collision is used when the number of particles is too large to track individually. It calculates the probability of particle collisions and their outcomes stochastically. The breakup model caters to the fragmentation of particles due to the aerodynamic instabilities or impact with surfaces or other particles. And the last option, which is volume displacement, considers the volume occupied by the particles, preventing them from occupying the same space at the same time. It's useful when the volume fraction of particles is high. Each of these models adds a layer of complexity and realism to the simulation, allowing for more accurate predictions in multi-phase flow problems. However, they also increase the computational cost and the time required to solve the problem. The next tab is the UDF. The User-Defined Functions tab in the Discrete Phase model window allows users to customize the behavior of the software. This is especially useful when the built-in features of ANSYS Fluent do not meet the unique requirements of a particular simulation. Here also we have the numerics. This tab is used to control the numerical aspects of the DPM simulation. It allows you to set the parameters for the numerical schemes used to solve the equations of motion for the particles. This includes options for the integration method, the number of iterations, and the convergence criteria. And finally, the parallel tab is used to control the parallel processing setting for the DPM simulation. It allows you to specify how the computational workload is distributed among the available processors. This includes options for the partitioning method and the number of partitions. After modifying the discrete phase model window options, we can go to the injections to define our injection. Here you can see that the injection 0 is defined. And in this new window, we can take a look at it. In ANSYS Fluent, there are several types of injection you can choose from. Here you can see all the types. A single injection introduces a single particle into the system. A group injection introduces a group of particles into the system. All particles in the group have the same properties and initial conditions. The number of particles in the group is specified by the number of streams. A surface injection, which is selected for this simulation, introduces particles into the system from a surface you specify. Here, the inlet surface is selected for injection. You can specify the total mass flow rate, velocity, magnitude, and the diameter of the particles. Here we have the cone injection type. A cone injection introduces particles into the system from a cone-shaped region you specify. You can specify the cone's base center, base radius, and axis direction. The next option is plane orifice atomizer. The plane orifice atomizer is the simplest form of atomizer. It consists of a simple round orifice through which the liquid is discharged. The spray is formed by the disintegration of the fluid jet due to disturbances in the liquid flow. The atomization process is primarily due to the aerodynamic interaction between the liquid jet and the surrounding air. In a pressure swirl atomizer, the liquid is fed into the swirl chamber under pressure and exits the atomizer through a small orifice. The high pressure and swirling motion of the liquid causes it to form a thin conical sheet, which subsequently integrates into droplets. This type of atomizer is commonly used in gas turbine engines. The air blast atomizer uses a high-speed air stream to atomize the liquid. The liquid is introduced into the air stream, which causes it to break up into fine droplets. This type of atomizer is often used in applications where fine, low-velocity spray is required. A flat fan atomizer produces a flat, fan-shaped spray pattern. The liquid is discharged through a narrow, elongated orifice, which causes it to spread out into a thin, flat sheet. This sheet then breaks up into droplets, forming a flat, fan-shaped spray. The effervescent atomizer uses a gas, usually air, to atomize the liquid. The gas is bubbled through the liquid, causing it to become saturated with gas. When this gas saturated liquid is discharged through a nozzle, the rapid expansion of the gas causes the liquid to break up into droplets. A file injection introduces particles into the system based on a file you provide. The file contains a list of particles, each with its own properties and initial conditions. And the last option is condensate. The condensate injection is typically used in simulations involving multi-phase flows where a phase change such as condensation or evaporation occurs. This injection type is specifically designed to model the injection of a condensate substance formed when a gas or vapor is cooled or compressed and changes its state to a liquid into the system. After that, we have the particle types. Here we have the massless, inert, droplet, combusting, and multi-component options. Massless particles are used for tracking purposes only. They do not contribute to the mass, momentum, or energy of the continuous phase. This model is useful when the mass loading of the particles is low and the particle influence on the fluid phase is negligible. Inert particles are those that do not undergo any chemical reaction during the course of their travel. They can exchange momentum and energy with a continuous phase, but they do not exchange mass. Examples include solid particles like sand in airflow. Next one is droplet. Droplet particles are a type of inert particle that can change phase from liquid to gas or vice versa. The droplets can absorb heat from or lose heat to the continuous phase, causing them to evaporate or condense. This is commonly used in spray modeling. Combusting particles are particles that undergo combustion or other chemical reactions. These particles can exchange mass, momentum, and energy with the continuous phase. This is often used in modeling coal combustion or spray combustion. Multi-component particles are composed of more than one material. They can undergo mass transfer with the continuous phase and between the different components of the particle itself. This is used in modeling processes like drying, where a volatile component of the particle evaporates into the continuous phase. Okay, here the material is defined as impurities and the diameter distribution is uniform. This is the diameter of the particles, velocity magnitude, which is 0 and will be driven by the fluid flow or the continuous phase, and the total flow rate is here. Also, the inject using phase normal direction option is enabled. After the models, we have materials. By double clicking on materials, we can see all the materials defined for the project. In fluid section, the natural gas is defined. By clicking on it and hitting the create edit option, we can see that its name is natural gas. This is the chemical formula, and here the density and viscosity of the material is defined. For the solid, the aluminium is defined, which is not necessary for our project. And here under the inert particle, the impurities is defined. Let's take a look at it. Its name is impurities, and here's the chemical formula. You can leave it blank, and here's the density of the particle. Also, you can import some predefined materials from the Fluent database, and here you can search the name of your material. After defining our materials, we can assign them in cell zone conditions to our zones. Here, as you can see, we have just one zone. and its material is the natural gas. There isn't another option here, so close it. The next option is to set the boundary conditions. Here I double click on it. In order to classify them based on their type, I hit the zone type option. And here it's visible that we have one inlet boundary condition, one interior, one outlet, and two wall boundary conditions. To take a look at inlet boundary condition, click on it and hit the edit. In the momentum tab, which is the first one, the velocity magnitude is set to 5 meter per second. Also, the specification method is intensity and hydraulic diameter, which is the diameter of the inlet boundary condition. In the DPM tab, we have to set the discrete phase boundary condition type, which is set to escape. Here the first option is reflect. In this boundary condition, all particles that hit the boundary are reflected. This is similar to a perfectly elastic collision where the total kinetic energy is conserved. The direction of the particle after the collision is determined by the angle of incidence, similar to a light ray reflecting of a mirror. Usually the wall boundary conditions are in reflect type. The trap boundary condition immediately terminates the trajectory of any particle that hits the boundary. Essentially, the boundary traps the particle, removing it from the simulation. This can be useful for simulating filters or other situations where the particles are permanently removed from the flow. The escape boundary condition allows particles that hit the boundary to escape the computational domain. The trajectories of these particles are terminated, but unlike the trap condition, it is assumed that the particles continue to exist outside the domain. The inlet and outlet boundary conditions usually are in type of escape. The wall jet boundary condition is used to model situations where a jet of particles is emitted from a boundary. The direction and speed of particles can be specified, allowing for a wide range of jet behaviors to be simulated. And finally, the user-defined boundary type. This boundary condition allows for custom behaviors to be defined by the user. This can be used to model complex particle interactions that are not covered by the other boundary conditions. The behavior is specified using UDF or user-defined functions, allowing for a high degree of flexibility. In case of interior boundary condition, there is no option to change. For outlet, in momentum tab, just make sure that the gauge pressure is set to 0 pascals. The intensity and hydraulic diameter is selected. The turbulence intensity is 5%, and here the diameter of the outlet boundary conditions are entered. Also, the DPM discrete or the discrete phase boundary condition type is escape, just like the inlet boundary condition. Okay, we have two wall boundary conditions, which the first one is wall fin. To take a look at this boundary condition, these are the fins inside the device. And wall out. This boundary condition is wall out. First, let's take a look at wall fin boundary condition. In the momentum tab, the wall motion is stationary, and no slip condition is set for shear condition. In DPM tab, the discrete phase boundary condition is set to trap, and the erosion models, which are generic model, Finney, Oka, and DNV, are set to capture for the erosion models. The options in wall out is similar to wall fin. And that's it. Okay, the options in the setup section is investigated, and let's go to the solution part. Solution section, by double clicking on the first option, which is methods, you can see the solution methods in task page section. First, for the pressure velocity coupling scheme, the simple scheme is selected. The simple or semi-implicit method for pressure linked equations scheme is a numerical procedure used for solving the Navier-Stokes equations, which describe the motion of fluid. The scheme is iterative and relies on guessing and sequentially correcting the pressure and velocity fields to achieve a converged solution. It's widely used due to its simplicity and efficiency, especially for incompressible and steady-state flows. Under this scheme, we have the flux type. Here you can see that we have two options, which is distance-based and momentum-based. The Raychaud momentum-based and distance-based flux types are used for pressure-velocity coupling in simulations. The Raychaud momentum-based flux type is the original method, which is used to avoid the checkerboard pressure pattern by introducing a momentum interpolation term in the pressure equation. It works well for structured grids, but may not be as effective for unstructured grids. On the other hand, the Raychaud distance-based flux type is a more recent method that improves upon the original by taking into account the distance between cell centers. This makes it more effective for unstructured and non-orthogonal grids, leading to more accurate results. Both methods help maintain stability and accuracy in the simulation. In case of spatial discretization and gradient, the least square cell based is selected. This method for spatial discretization is an approach used to calculate gradient vectors for scalar quantities in the flow field. The method works by minimizing the sum of the squared differences between the values of the scalar quantity at the cell centers and the values predicted by the linear approximation of the scalar quantity over the entire cell. This method offers a higher level of accuracy compared to other methods like the Gringaus-based method, especially for unstructured and non-orthogonal meshes. However, it may require more computational resources due to its complexity. And for the pressure, momentum, turbulence, kinetic energy, and dissipation rate, standard and second order of wind and also first order of wind are selected. After methods, we have the controls. Here in solution controls, we have under relaxation factors, or the URF. URF is a numerical technique used to control the convergence of the solution in iterative methods. It's a factor by which the computed change of a variable is scaled down to avoid potential divergence or oscillations in the solution process. The range of under relaxation factors in ANSYS Fluent generally varies between 0 and 1. A value close to 0 means that the solution will converge slowly, while a value close to 1 means that the solution will converge faster, but it may lead to instability if the value is too high. The report definition is a specification that allows for the automatic calculation and reporting of certain derived quantities during the solution process. Here we have defined the y plus and area erosion. In turbulence field variable, the vol y plus is selected. We want to check the y plus on the vol in and vol out. The report name is y plus, and it will be reported in the plot. Also, the report type is facet maximum. It will show the maximum value of the y plus on the vol in and vol out. Also, we have the area erosion. Here is its name. Its report type is area weighted average. The field variable is discrete phase variables, or the DPM erosion rate in OCA model. And the value of the erosion will be investigated or will be reported on vol in and vol out. Also, the report will be shown on the plot. In the monitor section, we have the residuals. In ANSYS Fluent, residuals represent the imbalance in the solved equations and are used to assess the convergence of the solution. When the solution is perfectly converged, residuals would theoretically be zero. However, in practice, due to numerical errors and approximations, residuals tend to reach a small value and tend level off. The absolute criteria are defined here. And make sure that the print to console and plot options are enabled. Defining initial conditions for the computational domain is known as initialization in ANSYS Fluent, which is a crucial step in the simulation process. This step sets the starting point for the calculation. Here, by double-clicking on initialization, we can see the different methods. The standard initialization method initializes the entire domain with uniform conditions specified by the user. This approach is typically utilized when the initial state of the flow field is known. In contrast, the hybrid initialization method is a more advanced option that initializes the flow field based on potential flow solutions. This method is particularly beneficial in situations where the initial state of the flow field is not well known, because it can help the simulation reach a converged solution more quickly. Okay, here the standard initialization is selected. The gauge pressure, x velocity, and z velocity are set to 0, while the y velocity is 5 meters per second, which is like the inlet boundary condition. Also, the turbulence, kinetic energy, and dissipation rate have a small value. After that, you can hit the initialize, and in a few moments, the solution will be initialized, and it's now ready to run. Okay, here in the run calculation, we can enter the number of iterations. In ANSYS Fluent, iterations refers to the repeated process of solving equations to get closer to an accurate solution. The software uses an iterative method to solve the set of algebraic equations that are obtained from the discretization of the governing equations of the flow problem. The number of iterations are 10,000, and after that, you can hit the calculate, and the solution will be start to be solved. Okay, after about 5,000 iterations, the solution is stopped, and now we can extract the graphical views from the solution. In the results section, here I open the graphics, contour, and contour 1 is defined. Its type is discrete phase variable, and the DPM erosion rate with the OCA model. On which surfaces? The vol in and vol out. Save display, and here we can see the erosion rate on the surfaces of the vol out. If we disable the wall out, we can see the erosion on the wall fin. Okay, let's take a look at other options. Generic DPM erosion rate, Finney model, the McLaury, and also other parameters. For example, the velocity on the plane 4, here's the velocity magnitude on this plane. To define a plane, we can go to surfaces, right click on it, new, and define a plane. Here's the plane 4. Also, we can see the contour and the geometry at the same time by going to the scene. Here I enable the contour and there's no mesh, so I need to define a mesh here. That's it. I go back to the scene, contour and mesh. Okay, the contour inside the mesh is not visible, so I need to transparent or increase the transparency of the mesh to, for example, 60, and this is much better view. We can also save the picture in this window by clicking on the save picture option. Here we can set the format, the coloring method, the file type, and the resolution, which could be from custom to 4K figure. Also, this option is very useful, which will make the background white. In case of path lines, we can extract the streamlines from the solution. The path lines of the airflow from inlet, this is the trajectory of the fluid flow. By going to the scene section again, we can enable the path lines, save and display. And the last option is particle tracks, which tracks the particle motion of the solution. The color by type is a discrete phase variables, DPM velocity magnitude. The injection is injection 0, which is defined in the models. And save display. Okay, this is the trajectory of the particles into the domain. We can also change the track style, for example, to sphere. In the scene, I want to enable the particle track and disable the path line. And you can save pictures. Okay, I want to show you some of the figures that I have saved from the figures, and also the plot which was defined in the report definition section. Okay, the solution is investigated completely, and we have investigated the gas splitter device using discrete phase model using ANSYS Fluent